And of course, there's one more called the conductivity varies in presence of magnetic field, and this effect is called magnetoresistance. This effect is called magnetoresistance. Okay, so these are all just fundamental, what are certain properties of metals. Okay, and we will try to understand more about the free electron gas. Okay, the term called gas. We call it as a gas. Actually, we are not right now talking about the gas, but still we use the word called gas. What is this? Okay, this is a quite confusing term called gas. I'll tell you what. Gas, why we use gas? I'll tell you. See, suppose if you take a cylinder will have, let us say, gas particles. Okay, cylinder is filled with gas particles. Okay, gas molecules rather. Okay, and the molecules inside the gas cylinder will be they will be moving much faster. Okay, and they collide with each other, and of course they collide with each other, and of course they will be colliding with the walls of the container, and thereby even after colliding with each other, colliding with the container, they will not lose their velocities. Okay, and this one has been compared with a metal. Okay, a metal will have free electrons. The metal will have free electrons. So the movement of the electrons, or they will be rather more. Okay, much more. Okay, and they'll be moving much faster, and they will have the comparison here. Okay, so the metal has been compared with the molecules in a gas, and that's why we call it as electron gas. Now, most of the students generally what happens if you let's say the free electron gas, and suddenly all of a sudden there will be a confusion that what is this gas is all about. Okay, so once again, I just wanted to make it clear that we are talking about the gas in the sense like more number of electrons, free electrons are being present in metal, and that's been compared with the molecules in a container. Okay, and that's what is said to be the free electron gas. Okay, so slowly we try to understand the behavior of gases and the behavior, what are said to be the theory of free electrons in metals, and then Sommerfeld, for instance. Okay, we have Lorentz. Okay, for instance, we talk about now free electron theory. Okay, the gas, free electron gas. What are those free electron gas? And, it's postulates we try to understand. Generally, these postulates usually be someone is raising hand here. Anita Jyoti, also
Actually,
raising
not getting you. Yeah, your voice is breaking, sir. Not audible.
not audible.
Yes, sir. Signal is not yeah, from your side, sir.
Okay, that's why I asked you. When I started the discussion, I asked the first question that are you able to hear me? Okay, and what can I
Yes, your voice is breaking, sir. That's why I asked you.
are they? Then what can I do? Tell me. Maybe because of the signal, or I don't know. Okay, we'll see. Okay, if any improvement takes place of some time. Okay.
Okay, sir.
Okay. So the free electron gas. Okay, the free electron gas. Okay. Sorry. The free electron gas is as I said, like the electrons are all moving freely inside the metal, and they will be colliding, okay, with each other. And then here, the free electron gas. How we have to understand this concept? I'll tell you. The conduction of electrons are actually found to be they're completely free, and except for a potential at the surface. Okay, the electrons they'll be moving much freely. Okay, they will be moving much freely, and except for a potential at the surface. Okay, so what happens is it's like a see, metal is like this. We have a metal. Okay, the electrons are all moving here very much freely, and if they touch the top surface, they will get reflected. Okay, so that's what is usually described as, once again, the conduction of electrons, or they are completely free except for a potential at the surface. There will be some kind of resistance. Okay, only at the surface. Okay, and that's what it experiences. Okay, and the electrons, because of this, okay, potential at the surface, the electrons are confined in the interior of the metal. So we have here a metallic surface. Okay, metallic surface, the top one or the bottom one. Okay, and between the electrons, it moves much freely, and once it touches the electrons, touches the surface, then they'll experience some kind of a potential, and thereby they are being pushed down. Okay, and even at the bottom, from the bottom. So what happens is that the electrons are now being confined. Okay, the electrons are being confined, or are being restricted. Okay, and they cannot just escape. Okay, but they are bounded by some boundaries. Okay, that's how we have to understand. You have to understand that the electrons are now being blocked by something, or being blocked by the metal. Okay, metal surface. Okay, that's what you have to understand. And here, the conduction electrons, they are more or like as I already said, that they are like molecules in a gas, and they move inside the metal without any collision. Okay, without any collision. Sometimes they will be collided by reflecting from the surface. That's what I'm telling you, that it goes off, and there will be reflection, and then again come back, and again there will be goes off, and again there will be collision. And apart from that, and there is no resistance for that. Okay, and the conduction electrons are regarded as the free electron gas. That's what just now I told you, that the movement of electrons has been compared with the molecules in a container. Okay, gas molecules in a container. Okay, so please try to understand. There is no confusion. What I am telling is very clearly that the electrons in a metal are moving in such a way that they are moving much freely, and they'll have some kind of potential at the top and the bottom. Okay, apart from that, there is no exception, rather there is no resistance, and they'll be moving freely. Okay, and they are being compared with the molecules in a gas container. Okay, so that's what is been understood as. Okay, so that's how it just go into the much into detail of the properties of the metals. How does the electrons behaves inside the metal? Okay, and apart from that, that the conduction electrons will interact with the ions in the background. Okay, of course there will be always questions here, that why can't it be collide with the ions? Okay, of course they collide with the ions, and they collide with each other as well. Okay, while moving, they collide with each other as well, and the interactions are said to be here strong. The interaction are said to be strong, and the electrons are bound to suffer frequent collisions. They're colliding with each other, their interactions are taking place, and then there will be some interactions are said to be stronger if the interactions are said to be stronger. Okay, see here, if I say that the interactions are taking place very much stronger, and the electrons are moving freely, and this is controversial, isn't it? If I tell you that there are some interactions that take place very strongly, and still the electrons are moving freely, and this is said to be controversial. Okay? Instead, what happens is actually the interactions are observed to be weak. Okay, I'm very clear on what I'm talking. These interactions are said to be very weak. Okay, so please try to understand that the electrons are moving. Okay, they are moving, and they are moving much freely. Okay, repeatedly I'm telling that moving freely, and the interactions between the ion cores, okay, or colliding with each other. The interaction strength, okay, is said to be weaker, okay, much weaker. And then the electron, when it passes through an ion, for instance, then the velocity increases and rapidly enhances and decrease the potential. Okay, and then the electron spends only a small fraction of time near the ion, and most of the time it is far away from the region where the potential is said to be weak. Okay, so try to understand here that the electrons are moving much freely because electrons are moving much freely, and they don't spend much of the time with the potential, and the electron behaves like a free particle. Okay, and there are some reasons that the interaction between the conduction electrons and the electrons having a parallel spins stay away due to the Pauli's exclusion principle. Due to the Pauli's exclusion principle, and spins are opposite each other, and the electrons are come close to each other, then the Coulomb energy becomes exceedingly large, and which violates the tendency of electron system to have lowest possible energy. Okay, this is just see this free electron theory as part of the discussion of the free electron theory. First, we have discussed about the properties of metals, and then we slowly try to understand how the free electrons properties, or rather the free electrons behaves inside the metal. Okay, so we slowly try to understand more about the theories. Okay, theory which has been put forward by Drude Lawrence. Okay, Drude Lawrence free electron theory. This is said to be a very important question from the examination point of view. It's not only just examination point of view, but you have to, when you are understanding the metallic properties, okay, one after the other, you have to understand concepts of Drude Lawrence free electron theory. Okay, Drude Lawrence theorem. Drude Lawrence as a theory. What is that theory of free electron? How the free electrons has been discussed by, they have been put forward this theory by Drude Lawrence. Okay, clear. Okay, we'll have an understanding. Then, first of all, according to Drude Lawrence theory, a metal is supposed to consist of positive metal ions fixed in the lattice. Lattice, first of all, you have to know what is to be a lattice. Okay, lattice is atom or ion. Okay, an atom molecule, ion or molecule. We call it as a lattice. Okay, a metal is supposed to consist of positive metal ions fixed in the lattice, whose valence electrons move freely in the boundaries of the metal, like the gas molecules in a vessel. Once again, okay, um, the metal is supposed to consist of positive metal ions. Metal is supposed to consist of positive metal ions fixed in the lattice, whose valence electrons are move freely in the boundaries of metal, like gas molecules in a vessel. So the valence electrons, rather the outermost electrons, which can be able to move freely, and that's what we are talking about. And the valence electrons of the atoms become the conductors of electricity. So these are basic things which everyone knows. But still, the valence electrons or atoms become the conductors of electricity. They are, of course, they help to make the conduction, and they are called conduction electrons. Okay, the valence electrons are said to be the outermost electrons, are said to be the conduction electrons. Okay, and here, according to Drude Lawrence free electron theory, they applied the Maxwell's Boltzmann statistics. Yes, what is this Maxwell's Boltzmann statistics? What is this Maxwell's Boltzmann statistics? If you have studied anything about statistical mechanics, then you will be knowing this. okay, statistical mechanics, in which you'll be studying about the molecular properties, okay, molecules and their properties, and the statistics, okay, how the distribution takes place, how the molecules have been arranged, okay, the theories has been put forward, and Maxwell's distribution is one of them, okay. And here in this case, through Lorentz theory, Maxwell's distribution, Maxwell's Boltzmann statistics has been applied to the electron gas because, as I said, the electrons are all more large. They have been compared with the molecules in the component. Okay, they were really very much compared with the molecules in the gas containers. Okay, if the electrons are said to be same as the molecules in the container, then the Maxwell's Boltzmann statistics can be applied to the free electron theory. Okay, see, please try to understand what I'm talking about. See, metal, in the metal will have free electrons. The free electrons will have movement. And those free electrons are so much free that they are being compared with the molecules in the container. And the Maxwell's Boltzmann statistic has been applied. Okay, and further, the metal ions are bounded by the electrons by the electrostatic attraction um, between their positive charges and negatively charged electron gas. So there will be some kind of attraction. Okay, that's what we call it as electrostatic attraction between the positive charges and negatively charged gas. Okay, electron gas. Okay, and the forces between the conduction electrons and the ion cores are neglected. Already I told you that here, see how much of force which is acting between the conduction electrons and the ion cores has been neglected. If that quantity is said to be more, then the electron cannot move freely. So the conduction electrons, the forces between conduction electrons and the ion cores are said to be neglected. So according to this theory, okay, this theory, what is this? Drude-Lorentz theory. One after the other, one point after the other. Okay, I'm trying to tell you that first of all, they thought that these electrons are moving much freely, and they have some kind of a boundaries. Okay, they have some boundaries, like how the metal, how the molecules are moving in the gas. The gas will have boundaries, as a vessel will be acting like a boundary, and here the metal surface will be acting like a boundary. And the electrons will have, see here, as I said, like valence electrons playing an heavy role, and they will be acting like the conduction electrons. They are called, of course, the conduction electrons. Okay, and the forces between the electrons and the ion cores are they are neglected. Okay, the other way. And further, what I can say that the electrons are have much free movement. Okay, and here the Maxwell's Boltzmann statistics has been used. Okay, Maxwell's Boltzmann has been applied. Okay, so here the potential energy is neglected. Okay, and the one thing you have to keep in mind that the potential energy has been neglected, and the total energy of the electrons is kinetic. Okay, here the potential has been neglected, and the entire energy is to be kinetic. And in case of the room temperature, the currents also confined to the volume of the metal. They are being restricted by the volume of the metal, and of course they are not free to move outside the metal with the room temperature. The direct evidence of this fact is that the room temperature does not absorb the electron emission in metals. Therefore, so we can understand that inside the metal, potential energy of electrons at rest is lower than that of electron at rest outside the metal. So here, please try to understand here that the inside the potential energy of the electron is at rest is lower than that of an electron at rest outside the metal. Thus, the potential outside the metal may be taken as very high or anything. Okay, so potential. If you have studied anything for the potential, okay, and that this concept will be easy. Yeah, to quantum mechanics. There's a concept called potential wealth within these equations and potential wealth. Okay. If you have studied anything about that one, then it's very easy to understand. So, due to this high potential outside the metal on the surface, the conduction electrons remains inside the metal at room temperature. And for this high potential outside the metal, we assume that the metal surfaces are the sides of having here a sharp potential barrier. Okay, having here a sharp potential barrier. In that case, okay, in that case, if we try to apply the direction of the applied field. So if it is being applied, then the electrons are accelerated against the direction of the applied field. It is the collision with the massive atoms. The acceleration does not continue indefinitely. Mutual repulsions of the electrons are neglected because they do not transfer any momentum to the electrons in the direction of the applied field. If the electric field has what will happen? The acceleration does not continue. The acceleration, the acceleration does not. The acceleration does not continue indefinitely, and the mutual repulsions of the electrons are neglected because they do not transfer any momentum of the electron in the direction of the applied field. Okay. The momentum cannot be applied to the like momentum of the electrons in the direction of the field, and the mean velocity acquired by the electron the application of electric field. In simple words, try to understand that we have the normal movement of the electrons, and with the application of electric field, the electron velocity increases. Okay, and that's what we usually refer to as drift velocity. Okay, and this is superimposed over already existing random motion. Okay, and it is enhanced rather velocity. Okay, and this is what about the Drude-Lorentz free electron theory. Okay, Drude-Lorentz. Okay, see here. Generally, questions may be asked like discuss the properties of metals, and so also describe the free electron theory as proposed by Drude-Lorentz. So, like this question may be framed, and further, much theory is supposed to write. Okay. So as just now I discussed about. Okay. Like this, there are several things we can discuss about the free electron gas. Okay, and the free electron gas in which we have here the one-dimensional, two-dimensional theory. Okay, and the classical free electron theory. Okay, we have to have a discussion, or rather, sometimes there will be a question asking to compare the Drude electron theory with the classical free electron theory. Okay, there will be some kind of questions like this. They may be asking you to discuss the properties. Okay, to discuss the properties of metals, Drude-Lorentz theory of metals, or they may be asking you to write down the postulates of the electron theory. Okay, postulates of the electron theory. So looks like a very basic, but still have to understand. Okay, postulates. Let's see the classical free electron theory of metals. Classical free electron theory of metals. Okay, in an atom, the electron revolves around the nucleus. Okay, and the metal is composed of such atoms. In an atom, electrons move around the nucleus. This is a known fact. Okay, and the metal is composed of such atoms. Okay, and the valence electrons of atoms are free to move about the whole volume of the metals, like volume, like the molecules of a perfect gas in a container. This is what I have been telling since the beginning. Okay. Uh, so, the discussion. Okay. In the postulates, we try to understand that in an atom, the electron revolve around the nucleus, and the metal is composed of such atoms. Okay, and the valence electrons of atoms are free to move about the whole volume of the metals, like molecules of perfect gas in a container. It's been compared to the container, gas molecules in a container. Okay, and the collection of valence electrons from all the atoms in a given piece of metal. And it's not like just one or two electrons, but collectively the valence electrons have been collected. Okay, and collectively they form electron gas. Okay, it's said to be electron gas, large in number. In simple, the electrons are large in number and collectively called electron gas. Okay, and they are free to move throughout the volume of metal. Through the volume of the metal, that's what I said. Except at the surface, they'll have a potential on the top and also on the bottom. And these electrons, they are already said they will be moving much in what is it to be here random. Okay, they will be moving. They will be moving in a random direction. They'll be moving this way, that way, all the directions. They'll be moving around, and they collide with each other. Okay, and they collide with each other, of course, and they collide with the positive ions fixed to the lattice or other free electrons. Okay, they collide even with the positive ions. Okay, positive ions fixed to the lattice or other electrons. And all the collisions are said to be fairly elastic. Elastic. Elastic in the sense that there is no loss of energy. Okay, there is no loss of energy while they are colliding with each other. Okay, that you have to keep in mind. Okay, right. And further, the movement of free electrons obeys the laws of classical kinetic theory, almost like kinetic theory of gases, molecules in a gas. That's what I told you, that they follow how the kinetic theory of gases has been studied. And here, the movements of free electrons obeys the laws of classical kinetic theory of gases. And further, the electron velocities in the metal obey the classical Maxwell-Boltzmann distribution of velocities. Okay, as I said, in statistical mechanics, you will be trying to understand more about the distribution of molecules and how distribution of molecules, and by statistical method, which is being put forward by Maxwell and Boltzmann, and same is the case here. Okay, so that's the theory has been put forward and used in this case. Okay, where the electrons are moving and in a metal. Then free electrons move in a completely uniform potential field. You also have to keep in mind that the electrons, they will be moving with the completely uniform potential field. And due to this, ions because of the ions fixed at some places, various places, at which the ions are being fixed, and the electrons through this impact of the interaction will be less between the ions and the electrons. Okay, and when the electron field has to fight, as we look at the metal, the free electrons are being accelerated in a direction opposite to the direction of the field. This is what the point is not to. In case of metal, where the electrons are moving, and there's right? And the free electrons have been accelerated in direction opposite to the direction of the field. And this is what the these are the postulates of free classical free electron theory. Classical free electron theory of minerals. So that is what things. Okay. And further, we have here so many things. For instance, we have that free electron gas. We have models. Okay. Okay. So before we actually talk about the models and all, then we quickly let us discuss about the electrical conductivity. Okay, electrical conductivity generally be asked in short questions. Okay, so electrical conductivity. This, of course, in metals, the electrons are moving freely through the crystal lattice, and in the absence of, suppose let us say that it's been in the absence of any external field, applied external field, the net current with the movement of electrons is said to be zero. Net current with the movement of electrons is in the absence of applied external field. Okay. The net current due to movement of electrons is said to be zero, and they move randomly in all directions. And in between two collisions, the electrons move with uniform velocity. The thing is that the electrons will have a uniform velocity, and during every collision, both the directions and the magnitude of the velocity changing. Okay, and further, Ruth made use of electron gas model to explain the electrical conductivity. This electrical conductivity has been put forward by Ruth. Okay, and he says that the Ohm's law governs the electrical conductivity in metals at constant temperature flowing through the wire is the proportion to potential difference of Ohm's wire. Okay, and further the current is due to the motion of the conduction of photons under the influence of electric field. Okay, the current is passing through the neutral is due to the motion of photons under the influence of electric field, and the electric field exerts some kind of a force. Okay, doing acting on, for instance, it is acting on the electrons in the form of small e and capital E. Okay, and small e is said to be charge, and the E is said to be the electric field. Okay, capital E is said to be the electric field. The accelerated electrons collides with the rest of the medium, and its velocity drops to zero due to such collision. Once again, the accelerated electrons collides with the rest of the medium. Okay, they'll be the rest of the medium. Hence, velocity drops to zero due to such collision. And because this field is acting, it's been due to the speed, again, accelerated acceleration will be expressed, and there will be some kind of force acting on the constant collision. So, as I said, the collisions will be expressed, some kind of friction will be expressed, and then consider the v as the velocity of the electrons, and also the time between the two constant collisions, and the frictional force can be written as minus mv by r, where v is said to be the effective mass by Newton's law. dv by dt is to minus e minus m d by tau, and v is said to be f minus e tau by m times e. Okay, this for the theory and the conductivity. Okay, and we have several theories. Okay, but we will focus on the things which are said to be here very important. Of course, we'll have the block theorem and all anyway, but Drude Lorentz theory, and then we have here the free electron theory in 3 dimensions. Okay, free electron theory in 3 dimensions, and of course we have Sommerfeld theory. Okay, Sommerfeld theory also we will try to understand theory first, Then we have in 3 dimensions, how it will be extended to 3 dimensions. Okay, we try to understand it. Okay, so let's have a look at the Sommerfeld theory. Okay, the Sommerfeld theory. Sommerfeld suggests the model in which the potential is set as constant in such metal. Okay, once again, that the potential is thickness constant in such metal, so that the force acting on the electron is zero. Okay, so the force acting on the electron is zero. Sommerfeld model in which the potential is thickness constant. What is the potential is said to be thickness constant, and the force acting on the electron is said to be zero. So one assumption, so which is put forward by Sommerfeld, he says that the potential is constant. Okay, so potential is constant, and the force is equals to zero in simple terms. Potential is said to be constant, and the force on the electron is said to be zero, and the electron cannot be observed at room temperature. It is evident that the potential energy of the electron at rest due to the metal must be lower than that of electron outside the metal. Okay, so one observation is made, and he has put forward a concept that the potential energy of electrons inside the metal is less than the potential energy of the electrons outside the metal. Okay, so this what the observation is put forward, and the metal is replaced by the box containing non-interacting gas of electrons, the free electron gas. The free electrons are not assumed together independent. Okay, so as the principle of the principle of potential in the potential energy box, and secondly, by considering the distribution of large number of electrons in thermal equilibrium states. So here the electrons are how the electrons be arranged in different states. Once again, the electrons are not assumed together independent as they are taken to obey the Pauli's principle. And further, Sommerfeld investigated the behavior of the electron gas by discovering the possible energy states of an electron, possible energy states of an electron box. And secondly, by considering the distribution of energy, number of electrons in thermal energy among these states, and the Sommerfeld model, I said that the free electron gas in one-dimensional potential box. Then he extended to one-dimensional potential box has been extended to the three-dimensional extension, three-dimensional box. Okay, and first in this case, we'll have a discussion in one dimension, how the energy levels and the density of states has been distributed in one dimension. Okay, then what he says is that the electrons has been confined in a box of, let us say, it's a box of length L, for instance. It is a highly imaginative. You have to start thinking about that. The box is said to be there, having a length of L, for instance. Since the potential energy of this crystal is said to be zero, then he has put some conditions. Okay, he has written some conditions. V of x. V of x means potential. The potential V of x is said to be here. Inside we are talking about. Inside is said to be zero. V of x is zero. That is potential inside the crystal is said to be zero for a condition. If x is lying between 0 and L. Okay, suppose that means within that within that band, or rather within that said to be here container we're talking about, okay, or v of x is to be infinity. V of x is said to be infinity. Okay? If x is very much less than 0 and x is very much greater than L. Okay, that means the potential is said to be max, or rather infinity, rather outside. Okay, just he has put the theory has been put in the form of equation. Rather, I don't say this is equation, but I don't say that this is an equation, but this is condition. There's a kind of condition. The potential P of x goes to 0 for x lying between 0 and L. Okay, that is inside. And the potential is said to be maximum, that is infinity. If x is less than or equal to 0 and x is greater than or equal to 0. So see here, don't get confused here. What are these x and what are these L and all? They are nothing else but some kind of a boundaries. Okay, some this and that boundary. Okay, the metal will have okay one coordinate. Okay, and the coordinate. That's what we are writing. And here this Schrödinger's equation has been applied. Okay, the Schrödinger's equation for the region where capital V is equals to 0. If the potential is equals to 0, then what happens? Then if you are aware about the Schrödinger's equation as you might have studied in your quantum mechanics, then d psi square n by dx square, d psi square n by dx square plus 2me by h bar square psi n equals to 0. This is general Schrödinger's equation. This is understood only when you have come across the quantum mechanics. Okay, the basics of quantum mechanics. If you study, then you must be knowing by this time about the Schrödinger's equation. What is this Schrödinger's equation is all about? Okay? What is this Schrödinger's equation? What is psi wave function? So you have to know. Okay, they will try to understand. Try to make you to understand what is said to be here. Psi is said to be a wave function. Okay, and Schrödinger's equation. It is actually what is this equation used for? It's actually the representation of a wave. Okay, it's a representation of a wave which is moving from one place to another place, for instance. Okay, that is represented by Schrödinger's equation, and for about in a region from one place to another place, in that space, a number of particles are being, let us say, moving from one place to another. This is the mathematical representation of how the particles are. Okay, that's what the Schrödinger's equation signifies. Okay, so d psi square n by dx square plus 2me n by h bar square psi n equals to 0. Okay, where En is said to be the energy of the electron in the state n. En is said to be the energy of the electron in the state n, and the equation is almost looking like a second order differential equation. And the second order differential equation will have the solution. The solution can be written as psi n is equals to a e power of ikx plus b e power of minus ikx, and k square is where k square is equals to 2me by h bar square. Okay, and here we have used once again psi n is equals to a e power of ikx plus b e power of minus ikx, where k square is equals to 2m by h bar square. Okay, where a and b are said to be constants, and the value of these constants can be calculated by applying some boundary conditions. Okay, so somehow we have to solve this by applying some boundary conditions. And how we will do it, let us see. The value of these constants can be calculated by applying the boundary conditions. For instance, psi equals 0 when x is psi equals 0 when x is equals to 0, and psi equals 0 when x is equals to 1. Okay, if you apply these conditions to the equation, k square is equals to 2m e n by h plus 2. Suppose if you apply that, okay, and we have here psi n is equals to a power of minus plus, sorry, psi n is equals to a power of I kx plus b power of minus I kx, where k square is equals to 2m e n by h plus 2. Okay. In that equation, if you apply the conditions of psi equals to 0 when x is 0 and psi equals to 0 when x is equals to capital, if that is the case, okay, then what happens? Then if we apply these conditions, we will be getting a plus b equals to 0. That's one condition. Okay, and the other one is a e power of ikl plus b power of minus ikl equals to 0. And from the one of the equations, we'll be getting a equals minus of b. And if you substitute this, then you might be getting like a power of ikl minus a power of minus ikl equals 0. Can take a as common, and from this we can say that either a equals 0 or e power of ikl minus e power of minus ikl equals 0. And because a cannot be 0, yeah, it's a constant, it cannot be 0. So e power of ikl minus e power of minus ikl equals 0. So e power of ikl minus e power of minus ikl can be written as ikl, which is said to be here kl equals to n pi, and k is equals to n by l, where n equals 1, 2, 3. Okay, and this equation will have a solution. Okay. Before that, here I would like to show this, okay, this equation, so that you'll have a more understanding of what I am talking about. Just a yeah, I would like to share the uh, sorry about the delay. And so this is what I'm talking about. Okay. Just a quick look at what I am talking about. They see the figure there. That's the electron theory, and as suggested by the Sommerfeld. So just Sommerfeld model. That is said to be the box. Okay, it's a box of length L. We call it as a length of L. Okay, box of length L, and having the potential here. These are the conditions for I'm talking about. V of x equals to 0, and for x lying between 0 and L, that means inside. Okay, that is inside, and V of x is said to be infinity, and if x is less or equals to 0, and if x is greater than or equals to 0. Okay, and the Schrödinger's equation, as I said, the Schrödinger's equation for the region B equals to 0 is d square, d psi square and pi dx square plus 2m en by x square sine equals 0, where en is said to be the energy of the electron in the state L, and the solution is given by, this is actually, see, the first time when you are looking at this type of equations, so it looks like a bit clumsy. But when you are practicing this, okay, and so it's one of the easiest equations, okay. And the solution has been given by psi of n is given by a e power of ikx plus e power of minus ik, where h square is given by 2 m e n by h bar square. H bar is given by h by 2, okay. And see the equations, number 1 and 2. And of course, A, B constants, as I said before. But A, B constants are to be found out. Further, the boundary conditions have been written. And psi equals 0 when x, and psi equals 0 when x equals L. And applying these conditions, we may get here A as A plus B equals 0, one of the equations. Another one is A power of ikl plus B power of minus ikl equals to 0. And from the equation number 4, A equals minus 1B, and we put it back here, the value, to get A power of minus ikl minus A power of minus ikl equals 0. And here, either A can be 0 or E power of ikl minus ikl 0. And that can be written as sin kl equals 0. And kl will become pi. And k is equals to pi by L. So where n equals to 1, 2, 3, a different value. Okay, and the solution is being given by psi n equals c sin n pi by L, where of course c is constant, and the value of k square is given by n square pi square by L square, which is 2me by h bar square, and En, okay, energy levels. So that is what we are talking about. En is equals to n square h bar square pi square by 2m L square, where h square by 2m is being multiplied by n by 2m square. This is just simplification and right in that form. Okay, and this is going to be the equation for a quantum number n. Okay, and C has been chosen so that the unit probability of finding electron, okay, will be on the line. And this further we can try just to see this is how the values have been, okay, it's been taken on axis. Quantum number has been taken on the x-axis, and the energy shown on the y-axis. That's how the energy distribution will take place. And further, see, we have a condition here, psi conjugate psi of x, probability that the electron will be existing in that particular limit. Okay, and further, see integration between 0 and L. Okay, as I said in the theory, that the electron may be anywhere. Okay, may be anywhere. That's why integration has been taken everywhere, between 0 to L, anywhere. 0 to L. And psi n of x conjugate and sin of x dx is equal to 1. This is normalization. So if you are familiar with the quantum mechanics, and this is quite easy. Okay, so integration over 0 to L, sin of x conjugate sin of x is equal to 60 addition to integration. And further, c square sin square n times by L dx is written c square by 2 is sines. It's like a sin square x. Sin square x can be written as 1 minus cos 2x. Okay, that's how it's been written. Okay, for simplification. And further, it's been reduced. And c square by 2 is equal to 1. Or further, what we get is sin is equal to 2 by L over 2 by L sin L by S. Okay. So that's how we try to just okay. So that's how we try to understand the Sommerfield model. Okay, so the nodes and all okay, and okay, and proceeding through. Okay, then you always for you to go through the nodes and try to understand what we are talking about. That will be much easier. Okay. Likewise, there are some more topics. Okay, we can try to understand more. Okay. We have, as I said, the distribution, of course, and how the distribution the energy distribution is accessible, and with all the diagrams. If you draw all the diagrams, how the electron distribution takes place, will be interesting. Okay. Further, we have here to discuss many points. Of course, we can have some more discussion, maybe like in 3 dimensions. So this free electron gas in 3 dimensions. Okay, we will try to understand the concept. Okay, here not much of a difference. Okay, but the concept will remain same. Okay, okay. So free electron gas in 3 dimensions. What is this free electron gas in 3 dimensions? Okay, so first of all, to begin with, the electron behavior of metals, electronic behavior, how the electrons are being moving in the metals. And let us consider that the metal may be described by free electron gas, which is confined in a cubical box of length L. Cubical box has been taken, and the potential inside the crystal is said to be 0. Potential inside the crystal is said to be 0. Okay, so rather what we are talking about is we just slightly discuss the theory and put the same in the mathematical. We are trying to just put them in the mathematical form by writing the derivations. Of course, we do that. Okay. Before that, the assumption is that the potential inside the crystal is being taken. Okay. Inside the crystal, the potential is to be okay. Okay, right. As the time concludes, now the next class will continue. Thank you very much for joining.
Sir, please give me any notes, sir.
Sure,
Any
madam. See, as I said, don't worry about the notes.
Okay,
I'll be
thank you,
posting it.
thank you, sir.
Okay.
Okay, thank you, sir.